notice, and this is a typical copyright. We continue with mathematics syllabus for CSEC 2018 to 2027. Schedule of videos. Section 1, number theory and computation. All 33 of those videos have been published on YouTube in their entirety. Section 2, consumer arithmetic. All 12 of those videos have been published on YouTube in their entirety. Section 3, sets. This is the fourth of 6 videos on sets. The previous 3 have already been published on YouTube in their entirety. After that, by the end of December 2024, Section 4, measurement. Then January 2025, statistics. February 2025, algebra. March 2025, relations, functions, and graphs. April 2025, geometry and trigonometry. And finally, by May 2025, mid-May, vectors and matrices, and that will take care of all the objectives in this syllabus. Just a reminder again that I have divided section 1 into 33 videos, and all of those are available on YouTube in their entirety. This section, that is section 1, forms the foundation on which the rest of the syllabus is based. How well you can handle this section 1 will predict how well you will be able to do with the rest of the syllabus. So please make sure that you look at section 1, the 33 videos there, and understand them well, since that is needed to be able to do the rest of the syllabus. Reminder again, you need to know the times tables 2 to 12 if you already don't know those, especially since calculators are not allowed in paper 1. Section 2, consumer arithmetic. All 12 of those videos have been published. So with the 33 videos from section 1 and these 12 from section 2, 45 videos have been published on YouTube in their entirety, plus 3 more from section 3. That is to say, these 3 up here from section 3 have also been published in their entirety on YouTube. So this section has 6 videos only. Now, change of plan. Originally, I had said that I will publish up to video 3 in this section, plus the other 2 sections, in their totality on YouTube. But since these 3 videos will complete this section, I will also include those as free videos in their entirety on YouTube. These 3 here, I had originally said that they will only be partially available on YouTube, and that if you want to see them completely, you will be redirected to another site where a reasonable subscription fee is required. So, change of plan. All 6 videos in the section will be made available in their entirety on YouTube. Now, this plan will become effective from section 4, where only a few videos will be available in their entirety on YouTube, and the rest only partially available. If you want to see those complete videos, you will be directed to the site where a subscription is required. So for this section, we have completed these objectives, 1, 2, 3, and 4 in 3 videos. These 2 were done in video 1, and they were all published, as I said, on YouTube in their entirety. So we are now here Objective 5, which says describe relationships among sets using set notation and symbols. And the explanatory notes here is showing here more clearly: universal, complement, subsets, equal and equivalent sets, intersection, disjointed sets, and union of sets. Now, most of that we have already done in the first video. So we will review them and we will do the 2 or 3 new things listed here. So in addition to those terms that we just looked at, we need to know symbols and meaning when we are dealing with sets. And this picture here is taken from the syllabus, page 6. First of all, this one here means universal set. We have used that before. The second one here, union of sets. We have used that before. This one here, intersection of sets. We have also used that before. This stylized uppercase E means element of a set. This pair of braces here, or this Greek symbol here, which we'll talk about later, means the null or empty set. This one here means subset of. This A with something like an apostrophe, read as A prime, means complement of set A. And this X in this braces with an ellipsis here means the set of all X such that. We have met all of those before. We will review them and learn the few new things for this objective. So let's review universal set. The universal set and its notation. In objective 3.1, when we had to explain concepts relating to sets, one of those had to do with the universal set. And it says for any particular situation or problem, the universal set is the set that contains all the elements from which subsets can be extracted. It is denoted by this italicized uppercase U. For example, if the universal set has these elements here, 1 to 20, all answers required in this question will involve only those elements you see up there, 1 to 20. Even if you were asked, is 24 an element of U, you can only answer within the context of U, that is, within the context of these elements here. And of course, the answer to that will be no. Example, if the universal set has elements Andy, Isaac, Eric, Owen, Kyle, Lisa, Amy, Tina, Emily, Sarah, Melissa, Tracy, Andy, Pedro, and Kyle, then all answers required in this situation will involve only these elements here. That's for universal set. Remember, this is just a review. We did this in the first video in this section. Next, let's look at subset. Subset and its notation. Again, as I said, we did this in video 1 in this section. A subset is any part of the universal set. It exists only within the domain of the universal set. A subset is indicated by this symbol here, which looks like a stretched out C. For example, if the universal set has these elements and E has these elements, it can be seen that all elements in E are found in U. Therefore, E is a subset of U. Next, if U has those same elements we were looking at just now, 1 to 20 inclusive, and E has these elements, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, it can be seen that all elements in E are not found within U. Therefore, E is not a subset of U. If the universal set is made up of Andy, Isaac, Eric, and Owen, and R is the set Andy and Owen, since Andy and Owen are located within the universal set, then R is a subset of U. A subset of a given set is a collection of things that belong to the original set. For example, the subsets of the set A, which has elements A and B, are A by itself, B by itself, AB, and the null set. And that is an example and definition taken from your syllabus, page 67. If you find this video useful and interesting, please like and share. Like and share. You may also consider subscribing to this channel. Before we go on, what you see here are the 24 letters of the Greek alphabet. Now, we are not learning Greek. However, the Greek alphabet, many of which is used to represent items in mathematics and science. So what you see here is biblical Greek, not modern Greek. So the pronunciation would be slightly different. And I will just read them through quickly. And then we will consider those that are used in math and in physics. So you will know where these things come from, where you see them. So the first one is alpha, beta, gamma, delta, epsilon, zeta, eta, theta, iota, kappa, lambda, mu, nu, xi, omicron, p, I know we call that pi, but it's p, rho, sigma, tau, upsilon, phi, chi, c, and omega. So that's the Greek alphabet. It has only 24 letters. Now we will briefly look at a few of these that you already know and some that you will soon encounter. These first three here, the lowercase, alpha, beta, and gamma, those are used to represent the three types of radioactive emissions. The uppercase here for delta is used to represent a change in, for example, delta P is equal to rho G delta H in physics. Then we go to this one here, lowercase theta. It is used to represent an unknown angle, and you will hear your math teacher say and your physics teacher say sine theta is equal to 0.5 or something of the sort. Next one is this, lambda, the lowercase, wavelength of a wave, mu, the lowercase, which represents micro, as in a micrometer, 1 millionth. Next one is this one here. Its correct pronunciation is p, but I know in math we call it pi, and it represents 22/7, which is the ratio of the circumference to the diameter of a circle. So you say area is equal to pi r squared. Okay, we will continue saying pi in math, but if you are doing Greek, biblical Greek, that would be p. Lowercase, rho, is used to represent density in physics. Now, sigma here, this first uppercase here, is used to represent the sum of which is, as you could see here on the upper right corner in your spreadsheet program. And then the lowercase one here is used to represent standard deviation of a population, and we will meet that in math, though we don't have to do it in detail. Next one that we will meet is this one, which is relevant to our situation right now, which is fee, as in school fee. And in the next slide, we will actually see that. In your syllabus, it is written like this, but the truth of the matter is there's a slight error there. It should be written like this, somewhat stylized. However, if you see either one, you will know what it represents, the null set, and it's pronounced fee, as in school fee. And then you have omega. The uppercase is used as a unit of electrical resistance, like 20 ohms, shortened for omega, ohms. And this thing that looks like a W here is used to represent angular velocity measured in radians per second. I don't think you will meet this lowercase omega in physics or math at CSEC level, but you will meet them later on when you study higher. So that's just an overview in case you are doing physics and you are doing math and you come across these symbols and you're wondering where did they come from and what do they represent. This is where they came from, the Greek alphabet. Now, don't leave with the idea thinking that I can read biblical Greek. I can't. This verse here, John 1:1, in the original Greek, the English is, in the beginning was the Word, and the Word was with God, and the Word was God. Now, I can pick out a few of these words, like that one there, Logos, logos, and then you see it here again, logos, and you see it here again, logos. And I can also pick out this one, Theos, theos, which means God. And this is a variation of that. Instead of ending with an S at sigma, it ends with an N, nu. So I can pick out one or two words, but I can't read biblical Greek. So we continue with subsets. Continue. There are two special cases of subsets that we need to keep in mind. The first one is called empty set, which is a subset that has no element in it. It is indicated by the symbol, okay, remember what that is called? Phi, or empty braces. It's also called null set. So if all the elements are removed from U, we will still have a subset, but without anything in it. Even if that does not seem reasonable to you to call it a subset. So phi is a subset of U, or you could say the empty set is a subset of U. The other special case is that a complete universal set is also considered as a subset. So even if that does not make sense to you, and it does not seem reasonable that the whole set is called a subset. So yes, U is a subset of U. Now, those are two unusual cases. Bear those in mind. And that should suffice for review of subsets. Next, we are going to review complement. As I said, we did this in section 3, objective 1. So the complement of a set O, written as O prime, is the subset of all other elements in the universal set that are not elements of O. So in the previous example, we were looking at O being odd numbers from 1 to 20 inclusive. Then O prime will be the even numbers in the universal set of 1 to 20. As another example, if U is the universal set 2, 3, 4, 8, and 9, and P is the subset 2, 8, and 9, then P prime or P complement would be anything in the universal set that is not in P. So P is already 2, 8, and 9. So P prime will be 3 and 4. Another example that we already looked at, say these are the 3 children in a family. So the universal set is Peter, Carlos, and Julie. And let us say we have the subset sons, Peter and Carlos, then S prime or S complement would be the daughter, Julie. So complement, the complement of set A is another set of all the elements outside of A, but within the universal set. And that is taken from your syllabus, page 59, as a definition for complement. We continue with review union. And this was from objective 3.4, the last video we did. The union of 2 or more sets is a set that includes all the elements of these sets. Union is represented by this symbol here, which look like an uppercase U. So if the set P has elements A, B, C, and D, and the set R has elements C, E, F, and G, then if we were to find the union of P and R, we will list all the elements in P and R once. So A, B, C, D, that's from P. And from R, since we already have C listed here, we will not list C again. We will just list E, F, and G. So if an element is present in more than one set, it is listed once in their union. Let's look at another example. If the set V has elements A, B, C, D, the set X has elements E, F, G, and C, and the set Y has elements E, H, K, D, and R, then we can say that V union X union Y would be all elements in those 3 sets listed once. So we have A, B, C, D there. In this set, we have E, F, G. C is already listed, so E, F, G. And in this set, we already have E listed. We have D listed. So we will just take H, K, and R. H, K, and R. Now we will look at intersection of sets. Again, we are still on review. We did this already. In this same section, objective 4, which is the last objective we did, determine elements in intersections, unions, and so, well, right now we are dealing with intersection. Now, the intersection of 2 or more sets is the set that includes only. Previously, we were looking at union and we said that includes all. Now, with intersection, that includes only the elements common to all the sets. The symbol for intersection is this inverted U. So, let us say grade 9 students of this school who play in the cricket team and on the volleyball team. For cricket, we have Andy, Isaac, Eric, Owen, Kyle, Lisa, Amy, and Tina. And for volleyball, Emily, Sarah, Melissa, Tracy, Andy, Pedro, and Kyle. Now, what elements are common to both sets? Okay, sorry that I'm calling students elements here, which sometimes happen when teachers are frustrated with some troublesome students. So, let's continue. What elements are common to both sets? If you look carefully, there is Andy here. Do we have Andy anywhere in the second set? Yes, here. Isaac, no. Eric, no. Owen, no. Kyle, yes, Kyle is there and Kyle is here. Lisa, not playing volleyball. Amy, not playing volleyball. So, those 2 students, Andy and Kyle, we could say those 2 elements, are common. So C intersection V would be the subset made up of Andy and Kyle. We are still on intersection of sets and its notation. And we continue from the last video. And as we said, the intersection of two or more sets is the set that includes only the elements common to all these sets. The symbol for intersection is this inverted U. So if the set P has these elements, 2, 4, 6, even numbers from 1 to 20 inclusive, the set Q has these members, which are multiples of 3 from 1 to 20. And the set R has these elements, assortment of numbers from 1 to 20. What elements are common to all three sets? Consider carefully 2 in the first row in P. 2 is here, but 2 is not in Q. And so on. You will see that there is a 6 here, a 6 here, and a 6 here. There is a 12 here, a 12 there, and a 12 there. And there's an 18 here, an 18 here, and an 18 here. And nothing else is common to all three sets. Therefore, P intersection Q intersection R would be the subset that has elements 6, 12, and 18. That is intersection. So as of now, we have looked at universal set, union, intersection, elements, null set, subset, complement. So we still have this one more to review. We have looked at that before. So we just have this one here to review, which we will do now. In objective 2, first video in this section, you were to represent a set in various forms. And the syllabus lists 3 forms. First form is description. You could say a set A comprising of the first 3 natural numbers. You have described the set. It's precise, it's concise, and it's unambiguous. That's the first way. The third way, by listing all the elements. The set A is equal to 1, 2, 3. Those are the elements. Those are fairly easy. The next one is a little more complicated, where you use set builder notation. This one is somewhat tricky. A symbol is used to represent the element, which would be X, then a colon, followed by the range of X, and finally, X is a member of what group? So you would read this that you see up here as A is the set of all X such that 0 is less than X, which is less than 4, while X is a member of natural numbers. That's how you would read this. Now, there is an alternative reading to it. A is the set of all X such that X is greater than 0, which means we are beginning to read from the X point. And we go to the left, X is greater than 0, and then we come back to X is less than 4. In other words, A has members that are natural numbers between 0 and 4, which would work out to be 1, 2, and 3. So those are 3 ways of saying the same thing. But as I said, this B here is a little more complicated. So we now consider other relationships that we have not met before. So all along the line, so far, we were just reviewing what we learned before in this section. Now we want to talk about disjointed sets and its notation. So disjointed sets are 2 or more sets that have no element in common. In other words, their intersection will be phi, or the null set. We have met this concept before when we considered the empty set, but we did not learn the specific term for it. And now we are learning the term is disjointed sets. For example, if the set P has these elements, which are the even numbers from 1 to 20 inclusive, and the set Q has these elements, which are the multiples of 3 from 1 to 20, and the set R has these elements, an assortment of numbers from 1 to 20, then if you ask yourself, what elements are common to all three sets, all three? You look at them carefully and you find that actually no element is common to all three. Therefore, P intersection Q intersection R is the null set. Remember that symbol is phi, which is a null set. P intersection R. Let's just deal with P and R. Again, we have no member common to both of those sets. So P, Q, and R are disjointed sets taken together. P and R are disjointed sets. However, P and Q are not disjointed sets, as P intersection Q has three members: 6, 12, and 18. So I hope you understand what we mean by disjointed sets. They have no member in common, therefore their intersection is the empty set, the null set. From your syllabus, it says disjointed. Two sets are disjointed if they have no common elements. Their intersection is empty. That's from page 60 of your syllabus. That's a definition for disjointed sets. Consider the three sets shown below. Those who play cricket, those who play volleyball, those who play football from that school we were talking about, are C and V disjointed. C and V. We have Andy here. Do we have Andy down here? No. Isaac is here. Do we have Isaac here? No. Eric is here. Do we have Eric here? No. Owen is there. Do we have Owen here? No. Lisa is there. Do we have Lisa here? No. Amy is up there. Do we have Amy down here? No. Tina is there. Do we have Tina in the volleyball? No. Colin for cricket? Colin in volleyball? No. So the answer to this question, are C and V disjointed? The answer is yes, because there is no element common to C and V. Next question, are C and F disjointed? So you have Andy there, and we have Andy here, so we can stop right there. There may or may not be other common elements, but once we meet one element in C and that same one in F, we are not asked to list all the elements that are common in C and F. All we want to know, are C and F disjointed? And since Andy is in C and Andy is in F, the answer is no. Next question, are V and F disjointed? V and F. So let's see. Emily is there. Emily is nowhere down here in F. Sarah is there. Sarah is nowhere in F. Melissa is here, and Melissa is here, so we can stop right there. The answer is no. V and F are not disjointed. Melissa is common to both of them, and there may or may not be others, but once we find one element common, that means that those two sets are not disjointed. Finally, are C, V, and F disjointed? We have Andy there, all three together. We have Andy there. We don't have Andy here. And well, we really don't care if Andy is down here. We want to have Andy in all three. Or we want to have at least one person or one element common in all three. And since Andy is not there in V, then straight off we know that the answer is yes. C, V, and F are disjointed because because there is no element common in all three. Now we need to talk about equal and equivalent sets. They are not the same thing. Two sets are said to be equal if they have the same cardinality, that is the same number of elements, and the elements are identical elements. Same cardinality and identical elements. Consider the three sets shown below. You have C, which is A, B, C, D, E, and F. V, B, C, A, E, F, D, and G. And F, P, B, R, S, T, A, and V. Let's consider C and V. C is equal to V for two reasons. They both have the same cardinality, 1, 2, 3, 4, 5, 6, 7 elements each, and also the elements are the same. A is there, which is here. B is there, which is here. C is here, which is here. D is there, which is here. E and E, F and F, G and G. It doesn't matter if the elements are not in the same order in V as in C. They are the same number of elements and the same elements. Therefore, C is equal to V. Let's consider now V and F. 1, 2, 3, 4, 5, 6, 7. Count the elements below. Yes, you have 7 elements also in F. But are they the same elements? No, for the simple reason that there is a P down here and there is no P up here. So, what is the relationship between V and F? They are not equal because while they have the same number of elements, the elements themselves are not the same. So V is not equal to F. However, V and F are equivalent sets. They have the same cardinality, the same number of elements, but not identical elements. And you write that, remember we need to know the notation. You write it like this. V is equivalent to F. That sign there is the tilde sign. Is the, if you have a keyboard, a computer keyboard, it's the top left key on your computer keyboard. So V is equivalent to F, not equal. Sometimes you would see it with this sign, two-headed arrow. That also means V is equivalent to F. Sometimes you may even see it like this, with instead of an equal sign, you have, so it's an equal with like a dash over it. That also means equivalent. So if you see any one of those, that means equivalent. Now, do not confuse those signs, the equivalent sign, with this one here, which means is congruent to. In geometry, when you talk about triangles, the sides and angles, and so on. And we will meet that when we come to do geometry and trigonometry. So I'm just warning you here that this sign here means congruent. And we have 3 different signs here for equivalent. Two sets are said to be equal if they have the same cardinality and identical elements. They are equivalent if they have the same cardinality but different elements. Consider these 3 sets shown here, P, Q, and R. Consider P and R. P there, and R here. Are they equal or are they equivalent? Well, let's see. It's a 2 there, a 2 here, a 4 here, a 4 here, a 6 here, a 6 here, an 8 here, an 8 here, a 10 there, and a 10 there. So they have identical elements and the same number of elements. So the relationship between P and R is that P is equal to R. Let's consider P and Q. That's these two. P has 5 elements, Q has 5 elements, but the elements are not the same. There's a 2 here, there's no 2 down here, and right there we can stop. So that because they have the same number of elements, but the elements are different, we can say that P is equivalent to Q, not equal to Q. Finally, let's consider Q and R, these two here. So let's see. Q has a 1 here, R has no 1. So we can stop right there. Their elements are not identical. They do have 5 elements each. So if they have the same cardinality but not the same elements, then they are equivalent sets. Now, just a thought. Suppose we had Y, which had 6, 8, 10, 4, 2, and 9. Now you could see that this has 6 elements. So straight off, no idea of equality or equivalence would come into play, because P, Q, and R, they each has 5 elements, whereas Y has 6 elements. So nothing about equal or equivalent. And that brings us to the end of this objective here, objective 5. Describe relationships among sets using notation and symbols. And we reviewed universal set, complement, subsets, intersection, and union of sets. That was reviewed. What was new was equal and equivalent sets and disjointed sets. So in addition to all the symbols seen here on this page, we also learned equivalent symbols with that, this, and this. If you see any one of those 3, it means equivalent, not equal. So that brings us to the end of this video, which is video 4, based on objective 5 in section 3.